and online, and also for future viewers as well. Thank you for watching this. So yes, I'm going to be talking today a little bit about the work that we have been doing in Zaragoza, that we have done regarding learning to control large teams of robots. Okay, like these videos here, I will provide more context later on about the motivation for these videos. Just for the audience that doesn't know, no, because in Spain typically you know Madrid or Barcelona, so Zaragoza is just in the middle between the two of them. We are the fourth biggest city of Spain, big enough, good to live. I'm part of the university in the School of Engineering and Architecture and in the Computer Science and System Engineering department. I'm also part of the Robotics, Vision and Artificial Intelligence group, where we are mostly around 65 people, more or less, half and half faculty and students. And so before talking a little bit or more in detail about the learning to control large team of robots, also I would like to showcase or highlight very quickly some other projects that we have done, also to put in the spotlight other students that have worked or currently work with me. So some of the things that we have done with Pablo Puello, that he's now a postdoc in Sevilla, this is also a collaboration with MAC, is developing solutions for autonomous drone cinematography, where the main idea here was that on top of controlling how a drone should move to take images, what we did is, in the problem of cinematography, cameras in cinematographic setups are more advanced than the ones that we use in robotics. Typically, they have the focus distance, focal length, the aperture, the parts of the image that are in focus and out of focus. And the idea here was that we developed a couple control solution where we were able to obtain cinematographic effects. Like here, without moving just the drone, we were able to decide in an MPC framework whether we want the bottle to be on focus or the car to be on focus. We can see in the license plate. So this is one of the things we did or we are doing. We have also worked in distributed tracking and classification, where here the idea is that we have tried to combine, let's say, control theoretical methods like distributed Kalman filtering, where typically from a theoretical perspective, they focus more on the distributed aspects. But when you try to extend this or use this in real tracking scenarios like here, you need to deal with data association, bandwidth, and these kind of things. And this is what we did. The idea here is that each camera is performing the tracking individually, but by local information exchange, they somehow obtain some global coherent information. We extended this to an active perception setup, where some of the cameras can be static, but some other cameras can be mounted on drones. And the idea here is that how to somehow define or design motion strategies to obtain good measurements in terms of perception of neural networks or whatever, like here. This is a classification problem where you want to somehow determine the brands of the people, and then you combine static cameras and dynamic cameras for doing that. Following up in this line of research of active perception with David Morilla, that is last year a fourth-year PhD student in Zaragoza, we have been working on this active perception problem. The idea is that nowadays in robotics, if we use computer vision, it makes the most sense to use state-of-the-art neural networks to obtain these features, that semantic, open-world features. The idea is that from an active perception, as opposed to geometric methods, where you know that if you move the robot to one position or another, you are going to know the quality of the measurement that you are going to obtain. That's not that clear when you somehow have a complex, a powerful, big neural network. So what David did was developing representations that for the moment they are handcrafted, but we are now extending this to learn and open world solutions, where basically the idea is that we reason over which are the best positions that the robot should move to take measurements that, in terms of the output that the neural network provides, how they are useful. Here the example, typically if you want to somehow classify whether you have a glass or a mug, the idea is that typically a computer vision just focus on the image. When you have a robot that it can move, the idea is that probably if you know that you need to look for the handle, that's the kind of thing. And also we have worked on, just to get closer to the project that the projects that I want to talk about, optimal collision avoidance. this by Edu Sebastian, that is currently a postdoc in Cambridge, in Amanda Prorock's lab, the idea of navigating in dynamic environments where, as opposed to other reciprocal collision avoidance algorithms, what we developed here was a solution where you don't know the intention of the other agents. No? The idea is that you make the decisions based on pure onboard sensing, estimating how collaborative or not collaborative are other people. No? It's like when you consider navigation in real environments with people, some people will be looking at the cell phone, probably they don't make any effort to avoid you. Other people will be very conservative because of personal space. So try to estimate this from onboard perception to make decisions. That's more or less one of the recent works that we did. And this somehow helps to talk about the next question. No? So the idea of when you consider moving in a dynamic environment, controlling one or multiple robots in a dynamic environment, the idea of understanding how all the other agents are gonna react or interact is a very important problem. And if you consider, no, there is, from a distributed control perspective, this is a well-studied problem where there are models like flocking models, consensus models, no, consensus algorithms, that they are very simple, distributed in nature, they work very well. But if we look to this kind of videos, probably what happens, no, what we can guess is that these models, as the way they are not going to be enough to predict the behavior of how some agents interact with others, either because of animals, that they might be influenced by external factors, or in different human scenarios, where the idea here is that the interactions can be very, very complex. And some of these handcrafted classic algorithms like flocking, while as a good starting point, they are not enough. So the first research question that I want to talk to today is how to efficiently learn some kind of multi-robot policies that are capable of modeling these complex interactions, okay? So we are going to focus, we are going to try to extend to a learning setup rather than handcrafting. So this is also a work mostly done, or mainly done by Edu Sebastian, Carlos, who is co-advisor with me, or was co-advisor, and this is a work done in collaboration with UCSD, with Nikolai and Tai. Okay, so kudos, yes, I would say here, main effort to Edu. So first, when we think about how these analytic distributed controllers work, we have some requisites, and the idea is that if we want to replicate or obtain a learning-based solution equivalent, there are some properties that we need to consider. So what are these properties? The first one would be scalability. Especially this in a distributed control setup might be not important because they are made by design, but in learning it's important in the sense that we can consider architectures where, okay, we throw to the architecture the whole, let's say, multi-robot, multi-agent state and somehow predict the motion of everybody. But this imposes some problems in terms of scalability. What we would like is to have solutions that somehow are able to work or are valid for 3 or for 30, for 300 or for 3,000 robots. The video of the ship. We don't want to learn a model that predicts the herd behavior. We want a model that predicts the ship behavior so that we can use this model for an arbitrary number of sheep. Second, we want this to be distributed. As we work, it's like even when we are multiple people, each robot or multiple agents, each agent has onboard sensing, local sensing. We cannot expect that every agent is going to be able to know or to observe everything. So we would like solutions where the behavior is predicted or learned considering only the locally available information that each agent may have, which is also somehow goes to the hand with the scalability in the sense that in order to be scalable, distributed execution is a good property. And coming or evolving this line of research from control theory, we would like, as opposed to other black box learning methods, some kind of explainability in the physical sense, I would say. So here, if we are in some cooperative transportation problem, there's going to be some physical properties of the object that we want to transport, or if we want to consider some kind of robots, they have physical constraints, some dynamic behavior that we would like to integrate or incorporate in our models. So the question is, how can we obtain or learn these policies considering these 3 properties? So let's go one by one. In terms of scalability, the The idea is that we would like, and we are going to develop local policies, no? As opposed to somehow throw all the information into a big neural network or machine learning algorithm to predict the motion or the intentions of all the agents. We are going to work on solutions at the individual level, where there might be some local information, either by means of communication or perception. We will talk about that. But the idea is that we are going to have a per agent policy. Here we are going to assume homogeneous policies. So the idea is that this policy is going to be the same for all the robots. Okay? For distributed execution, we are inspired by how LLMs work, no? Like ChatGPT and self-attention. So the idea here is that we want to consider local information, but this local information is something that we would need to consider that is not constant or the same for each robot, no? Or for each agent. One agent may have available information of 3 neighbors, another one may have information available of 5 or 1 or none. So the idea is that we want a solution that is able to handle this time-varying neighborhood side. And self-attention in that sense is the natural or a very good tool because somehow it works with any number of neighbors. The intuition here would say that the same way that LLMs consider tokens, we can think words as tokens. It's not exactly like that, but we can think each word as a token. For us, we are going to consider each agent as a token. So when we are developing the policy or the model for the robot I will have their own information, and by perception or by communication, this is the information available, these 3 neighbors. It has no information about the red agents. The idea is that using self-attention, we obtain a matrix, no, an intermediate matrix that somehow weights the relationship of each of these tokens with each other and somehow outputs a vector of the same dimension. The important thing is that this dimension can be arbitrary. Okay? And finally, for explainability in the physical sense, we are going to use differential equations. In particular, what we are going to consider is a Port-Hamiltonian system. No? We are going to model the behavior of the multi-agent system as a Port-Hamiltonian system, where these are the dynamics, where we have the state vector. It can be whatever in our experiments and our setup is position and velocity of each agent. And then we have the interconnection and dissipation matrix and the Hamiltonian, which somehow represents the total energy of the system. And the idea is that this differential equation somehow is saying how the energy evolves as time moves. And with this dissipation, basically, it's somehow an equation that drives the system towards a minimum energy configuration. And then we have the input matrix and the local input. So the idea is that we are going to consider these kind of models where besides the physical properties that are very convenient for the setup, another important thing is that Port-Hamiltonian systems have very good properties in terms that, for example, the combination or the interconnection of a Port-Hamiltonian system is another Port-Hamiltonian system. So if we model robots as Port-Hamiltonian systems, or robots or agents, the union, the combination of multiple robots in an interactive way, it's another Port-Hamiltonian system. So these are the 3 ingredients. Now the question is, how can we put them together to obtain a full learning framework of distributed multi-robot interactions? So for the explainability, we are going to know, since we are using a physical differential equation, we are going to consider a physics-informed paradigm. No, the idea here is that opposed to classic physics, where these matrices are estimated either by system identification or because you know about the system, what we are going to do is we are going to parameterize them with this theta, no, with neural networks. We are going to learn, no, or we are going to compute the parameters that learn these matrices. Okay, that's the first question. So we are going to know our learning framework is going to be focused on learning the full matrix J, no, the interconnection, the dissipation, and this derivative of the Hamiltonian. Some things here. If you see, this is the full multi-agent system as opposed to the local individual system. As I said, because of the Port-Hamiltonian model, we can consider this. And the second thing that we are going to consider in our learning paradigm is instead of learning, let's say, the open loop dynamics of the agents, we are going to learn the closed loop dynamics, the desired closed loop dynamics of the task. Now, why are we considering this? Well, I will start with the middle scenario. Considering the closed loop dynamics, somehow by abstracting this thing, allows us, or it's a method that is well suited to learn from external observations. So I would say, if what we want to learn is to replicate this video of the ship, we have the video of the ship. So we know the ship, but we don't know the actions that the ship are applying. So the idea here is that way, we have a framework that we don't care about the actions, which might be very difficult to obtain from some demonstrations or from some videos or whatever. Also, we are somehow being agnostic to the robot dynamics, in the sense that here we care about the motion of the ship, and then if we want to replicate this or compute the individual actions for particular robots, this learning methodology can be applied to both a drone, a ground robot, an Ackermann vehicle with a steering angle and throttle, and whatever. Here, to do that, to transform the closed-loop dynamics into the open-loop dynamics and extract the local inputs, we can exploit another property of port Hamiltonian systems using passivity-based control. The idea is that under some conditions on the dynamics, the closed loop and the open loop, we are able from the closed loop to extract the open loop dynamics and therefore the actions that each robot needs to apply. Then, okay, so I'm saying that we are gonna learn the full, the multi-agent closed loop dynamics with this physics informed, but let's go from a global to a local. If we develop, for this example of 3 agents, if we somehow put this in a more, in an extended form, we have the evolution, the state evolution of each of the 3 agents, and we can consider here block matrices that somehow relate the different terms with the different Hamiltonians. So then, if we consider just this part, we obtain this equation. So the idea here is that in order to obtain a local policy, rather than learning the whole matrix J, the whole matrix R, and the whole Hamiltonian as one, we are going to learn individual, or our network is going to predict individual local submatrices. So that each agent somehow, by learning or by predicting these matrices, is able to infer their own closed loop dynamics and using passivity-based control, obtain their individual input. And finally, for a distributed execution, once again following up this, simply by noticing that, for example, if agent or robot 1 doesn't have information about robot 2, we can assume that our assumption is going to be that basically there is no relationship between the two of them. We can simply put these terms to 0, remove this term, and still obtain this. So the idea here is that we are going to learn the local matrices just of those agents that we have information about. Okay? And putting all together, the things about local policy, self-attention, physics informed, port Hamiltonian, closed loop, and all of this, basically we obtain the overall architecture that we are considering, where we have the multi-robot system, and then each robot in the system basically has their own information and information from neighbors, and what they are going to have is a self-attention that we are going to have 3 heads. One head to learn J, one head to learn R, and one head to learn H. Now here you can see also another property of the self-attention, basically because we are obtaining a vector with the same dimension of the input. There are some things here that if you go to the paper you can analyze, also other tricks, but the idea is that basically the whole architecture is providing all these matrices together. Okay, so one head is in charge using self-attention of inferring the whole row with the submatrices R, the other with the J, and for the Hamiltonian, we have an assumption of the Hamiltonian decomposed as the sum of local Hamiltonians, so that this simplifies in terms of the gradient computation. Okay. And then we can obtain from this closed loop dynamics, using passivity-based control, the local individual actions. We have tested this. First, we tried in an imitation learning framework. So the idea here is that we have demonstrations. You can imagine, here, sorry to disappoint, we didn't try this with the video of the ship because of other perception issues, but conceptually it's the same. This is the end goal. The idea is that in some kind of navigation and in some kind of flocking task, the idea is that we recorded some videos where we have known analytical controllers. These ones are distributed, but here I would argue, one of the things that we like is that we can consider a centralized expert. So we can develop some kind of centralized policy, obtain the demonstrations, and still learn how to distribute it. So in that sense, this approach has other properties that are advantageous from a practical point of view. And then basically with our laws comparing the predictive trajectories with the ground truth trajectories, we were able, learning from demonstrations of 4 robots, we were able to execute this policy in different numbers for 16 or up to 64. And the same with the flocking. Still, something regarding imitation learning, I would say is that you are conditioned by your demonstrations. So here, something funny that I want to point out. In the navigation is more or less okay. At the end of the day, they basically know how to avoid each other. Even when it seems that they collide, they don't collide. But it's more a matter of going in a straight line to the goal. But in the flocking, something interesting is that here what you see that they learn, rather than forming a lattice, they learn somehow to go around the center of them. So in that sense, still, from an imitation learning, the concept of getting good demonstration is important. Which is why we also moved, this was presented in ICRA, and then we moved and extended this to a reinforcement learning framework, where the idea here is that we developed a physics-informed actor critic, where the actor is the same architecture, this physics-informed multi-head self-attention, but the idea here in the reinforcement learning, assuming that you have access to the whole environment, there are some properties like, okay, the critic is the same, it can be centralized, any network, whatever, but in terms of the experiences and the reward, the thing is that even when you are considering local actions, somehow you can consider a global reward of all the multi-agent actions together, which somehow learns local policies based on global behavior, even if you don't have access to that information. And this we do by storing also in the replay buffer the whole thing. But also the idea here is that a whole multi-robot experience, because we have a single policy that is replicated among the multiple agents, we somehow backpropagate all the experiences of the multi-agent system simultaneously. Okay, so we get backpropagation of a full multi-agent experience at the individual level. And here we were able, using the VIMA simulator, to try a variety of problems. In all the problems, we were training with very few agents and then replicating the behavior in a larger number. So navigation, okay, coverage, transportation, or even a competitive scenario where it's a food resource gathering, where there are some properties in the game, like if one agent is alone and is approached by 2 or more agents of the other team, it gets disconnected. So what happens is that the blue team, our team, they somehow learn also as part of the policy, they learn to work together. And it works, training in a small setup, it generalizes well to a good setup. Again, there are still some things to consider, So I would say here regarding the scalability, still this is, up to our knowledge, the first policy that is able to generalize to different number of agents. But as you can see, for example, limitations I would point out in the coverage. We have trained with 3 agents, and what happens here is that some of the agents, basically they learn to do nothing. So some limitations, some room, some opportunities for people to keep working on this. And okay, more fun results about this. We also applied this in a physics, a realistic physics engine, so the half cheetah problem in Muyoko, where the idea is that we are treating, let's say, the joints as agents, and then the communication is defined by just the word consecutive, link, sorry, it doesn't come the word. So the idea here is that, and I will answer your question, we are able to learn also complex behaviors. It's not a full multi-robot setup, but still we treat it as a multi-robot setup and it learns. And more interestingly, also in a real multi-robot system with imperfect communications, with the important thing here is the zero-shot transfer, learning transfer. So we trained in the previous example in VIMAS with holonomic vehicles, and we were able to take the Robotarium simulator, which has non-holonomic robots, and the same policy, because of this agnostic to robot dynamics, we were able to translate it to this setup and even go to the real robots and being able to somehow still navigate. You had a question? Sorry, yes?
You differentiate each agent, or how do you cluster them to test?
in this one, if I'm correct, so the thing is that you have two teams, so you have two policies. Each robot in our team has the same policy, so they all have the same, let's say, neural network with the same weights. Now, the question is like, well, they know, yes, I would say that they know when, in the perception, they know whether the other agents are friends or enemies. And for the training, if I'm correct, we first train with reinforcement, classic reinforcement learning, a policy for the red team, and then we freeze it, and then we assume that the red team has this frozen policy, and then we use RL with our solution to train ours. Room for discussion here about the fairness, no? Because somehow we are adapting to existing policy that they are not, but that wasn't the, let's say, the main point of this. The main point was more in terms of the scalability and being able to show learning these behaviors in a scalable way. Yes?
So you mentioned it's robot agnostic, but does that work within the same team? Could you team aerial and terrestrial robots under the same policy, or would you have two separate?
We haven't tried, but I would argue that yes, you can, in the sense that at the end of the day, what you are learning is this. No, it's like what you know is how the closed loop behavior should be. And now, using passivity-based control, you have your own, you know your own dynamics. So if it's a drone and a ground robot, they know their dynamics. So the question is, what is the action that I should apply, knowing my open loop dynamics, to guarantee that the closed loop dynamics look like this? So yes, we haven't tried, but a heterogeneous behavior, no. Homogeneous behavior with heterogeneous robots, yes. Okay. Any other questions before I switch topics? No? There were two ideas. Okay, good. So far we have seen how to compute low-level control actions from these demonstrations or in this framework. But there is also another problem that we can address and that we address, that is also some kind of a high-level planning. So instead of just try to learn the low-level behavior, can we use existing or approaches, learning approaches, to learn high-level behavior, high-level planning? And here we address this in the problem of drone swarms and art shows. No? These drone shows where you see the shows. No? This is from a very recent or relatively recent video with, I think, 10,000 drones that they beat the Guinness World Record and they created this dragon. No? So the idea here is that when you consider this problem about displaying, no, or defining high-level goal solutions or high-level planning solutions for large teams of robots, typically this is a very complex problem. No? It's like if you want to develop this, probably there is a team of engineers spending a lot of time also design people, make it like that. So the question, no, the research question is, can we, no, how can we create and achieve these desired configurations for the multi-robots team in a kind of simple, that everybody can do way? No? And this, the idea was, no, or the motivation was, if you think about DALI, you provide a prompt and it generates a very complex image. So the question is, can we say, oh, I have these 1,000 robots and I would like a figure of a dragon. Develop me, no, the high-level solution to achieve this. So this is the research question that we addressed here. And this was a work mostly done, no? The main authors are Pablo and Carlos. Pablo now in Sevilla, Carlos still in Zaragoza. And Ruben and also Mac. No? This is another collaboration that we have with Stanford. And we have different approaches, but I'm going to just talk about the latest one, the swarms. So, okay, the idea here is, as I said, we wanted to extend the concept of DALI to a swarm. No? And for those, I assume nowadays everybody knows, and we have played, all of us, in more or less detail with DALI, no? Create an image of a cat controlling a drone, this kind of thing. So the idea is, can we use the same approach to control a swarm of robots? And more or less, this is what I'm going to be talking now very quickly, very briefly, to discuss with you. So just, I assume that, or probably a lot of people has the background, but just very briefly, let's talk about how a diffusion model works. No? So the idea here is that this is a self-supervised method where you start with different images, and the associated prompts, no? Like a kid surfing in the beach and a pangolin. And the idea is that the diffusion model, what it does to train is it generates, or it adds in a controlled way, an incremental noise to the pixels, no? So it's like it's noising the picture and this, the image, and this is something that you can do. And basically the diffusion model, what it learns is how it should denoise this, no? How much at each given time step, how much each pixel, how it should change to slowly converge towards the desired image. And the property is that by training with a sufficiently number amount of images and prompts, the idea is that this then allows to generalize to unseen configurations. So what it obtains, because it's a noisy, some kind of distribution, you can start now, no? The processing inference is that you start with a completely random image. Basically, from this completely random situation, you sample one point, and then you apply this diffusion, no, consecutive to the noise until you obtain the one. And the thing is that if you somehow initially sample a different random noisy image, you obtain a different random final image. Okay? So the question is, no, how can we move from images to swarms? And something natural that we can consider here is that at the end of the day, even when there is relationship between the pixels, we can think of the pixels as robots. No? At the end of the day, an image is a large amount of pixels, so a swarm is a large amount of robots. Let's treat the robots as pixels. But now, let's go step by step about how we somehow transform this problem. First of all, pixels are in the 2D space, drones are in the 3D space, so we don't want to generate 2D pixels, we want to generate 3D positions for our dragon. So instead of training over images, we are going to train over point clouds. And this is something that we found that the idea of generating, a generative model, a diffusion, a DDPM algorithm for point clouds was already available. So we started from this. No? It's ShapeNet with categories. And the idea is that these categories represent our final goals, figures of planes, of chairs, and so on. Taking this, the idea is that you start from a completely random point cloud, and then you converge in this model to the desired point cloud. The idea here, as I said, the high-level planning, I would say. So if we think about this as our planner, the idea is as opposed of the general diffusion algorithm that you don't care about the intermediate images, no? You care, it's like the random image that you don't care, the prompt, and what you care is just about the final image. For us, as roboticists in the high-level planner, each step is important. No? This is somehow giving us the plan that the robot should follow. So what happens if we try to do this? We are going to consider three metrics of interest from a robotics perspective. One, obviously, is the 3D shape quality, answer distance between the final point cloud that we obtain with the robots, moving the robots with their dynamics, versus the desired shape. But then there are two important things that in an image you don't have, but in a robot you have. One is collision avoidance. You don't care if two pixels have the same value, but you care if 2 points in the point cloud are in the same position, because that means a collision, two robots that crash. And then, as before with the physics-informed, here I'm not going to follow a physics-informed paradigm, but still robots have dynamics, so we would like trajectories that somehow are feasible or followable by robots. So if we try to somehow consider the previous algorithm as our reference trajectory to follow, what happens is that, yes, the shape quality, the final shape quality is very good because in 100 steps we reach this desired plane, but A, there are multiple collisions, and B, because of this wide noising, denoising methodology of DDPM, the idea is that this is not feasible to follow by a drone. The idea is that the drone should go up, then in the next step should go down, right, left, something that a drone cannot follow, unless you are very, very slow and you don't care about time. Okay, so what can we do? Let's somehow forget, it's like, okay, since we only care about the final configuration, forget about the whole pipeline of denoising versions, just focus on the final shape, and just apply a reactive navigation algorithm, like Orca, something similar. Here they are cooperative, so we don't need to go for Avocado or other unknown algorithms like the one I showed. We can go for classic optimal reciprocal collision avoidance, and follow it. No? So DDPM, 3D plus ORCA. And the idea here is that in terms of smooth trajectories and collision avoidance, it works pretty well. But at the end of the day, what happens? That if you consider what the DDPM is doing, it's moving a lot like that. But then if you only consider the final position and your position, the way these reactive navigation algorithms work, they are pushing all the time towards the final goal. So probably a good solution, a good trajectory for the drones would have some course, but you are trying to push directly towards your desired goal. So it's like all the drones are trying to move on a straight line towards the shape. And what happens is that ORCA is somehow, to prevent collisions, it's converging slowly. So if we give this algorithm the same amount of steps in terms of motion as the previous one, what happens is that we are not able to reach our desired solution. So it's slower. Not bad, but the quality under the same conditions is bad. So, okay, next step. No, a little bit more recently, in ICLR 2023, there were this other family of generative algorithms that they are conditional flow matching, that instead of considering discrete time steps and wide Gaussian denoising, they consider a flow equation. So basically they are learning the velocity at which the pixels should change in some sense. No? What you learn is this is in the continuous time, so you don't care about discrete time steps, and what you learn is the flow, basically the velocity of change. And then at inference, what you can do is this CFM model, you just integrate to obtain the same one. Conceptually, it's very similar, but this change to a velocity, what implies is that we are obtaining a smooth motion. And basically what we did here, no, we used that, but this was a contribution of ours. We translated this conditional flow matching of images. What we did is we extended it to point clouds. Here we didn't use, no, and this is more or less what you get. You get this kind of flow vector, no, flow space, where you learn where to move in a continuous time. And then the idea at inference basically is more or less the same. So what happens here is, once again, now the 3D shape quality is once again good. These are smooth trajectories in the sense that we have continuous motion, but still collision avoidance doesn't work. We have seen, no, we can say, okay, let's put the ORCA at the final configuration. We would have the same problem. So the idea here is the way ORCA works is you have this reference velocity and you try to move in the closest velocity that is safe. So instead of considering a velocity towards the final point, the final solution, what we call gen swarms, this is our approach, was to consider ORCA at each time step. So we have the desired velocity at each time step given by the conditional flow matching, and we put ORCA on top to apply the velocity that is the closest to the current one. No? So if we need to do this turn, we will try to do this turn, something the closest as it, so that we end up. The idea here, no, the high level from a robotics perspective intuition is that we are using the conditional flow matching as an online reference trajectory generator, no? The desired velocities to follow, and ORCA as the low level controller in the loop to apply the closest ones that are safe. And obviously, no, it's like what happens here is that we get 3D shape quality, smooth trajectories, and collision avoidance. Okay? So this is more or less the current state of this. We are now discussing, at the end of the day, still there are some things to consider here. No? Once again, the limitations. When you consider how the conditional flow matching trains, at the end of the day, it somehow still points, no, it tries to consider this straight line kind of motion, which is good in terms of performance of the training because somehow you can sample, but it's not actually considering robot dynamics. No? One would argue that a good algorithm, a generative algorithm, no? A Gen AI algorithm that considers robot should embed the robot dynamics some way. So this is something that we've been discussing, also how to make this dynamic to videos and so on. But still work in progress. And I'm actually very good on time. So I would just like to finish while acknowledging the funding. So Fulbright for this 6 months experience, and both ONR and the government of Spain for money for the grants to carry out this research. So basically, as take-home messages, I have presented to all of you 2 solutions to learn to control large team of robots, no? Both at the low level using a physics-informed approach for distributed control policies, where the idea is that we are combining physics-informed self-attention and a local solution to predict the low-level behavior of different agents, and also a generative AI algorithm to obtain high-level reference trajectories in the problem of drone art shows to generate these beautiful dragons. If you are interested in this research, you can go to our website. Also, I invite everybody to connect to me on LinkedIn. For the Stanford people, as Max said, I'm here until the end of the summer. I'm available. Feel free to contact me. I'm eager to talk to people. So I will always have time for a coffee or a friendly chat. And thank you very much. And I leave the room for questions.
I imagine it'll work anyways, but what if you start with a different drone swarm configuration that's not just randomized and then try and move to a different?
It doesn't work.
Oh, it doesn't?
It doesn't work, but why it doesn't work? That's a very good question. And here, yes, no lies, no, it doesn't work. We tried. The idea is we wanted to go from one to another, but the thing is that it's trained on, you start with the desired configuration, and somehow you assume a noise generation so that you end up in a uniform distribution of the drones. So if your initial distribution is not a uniform distribution, you have not learned how to move from one formation to another. We tried. So what we needed to do is go to the shape, go back, go to the shape. That's actually a big limitation in terms of drone shows for us here.
How do you think about like heterogeneous tasks within the swarm? So like within a swarm, you may need network relays to keep communication maximized across the swarm, or for like the naval demonstration, you might have gunships that have different tasks than observation ships. Like how would you think about that non-heterogeneous task?
For the first problem, to be honest, we haven't worked on that direction about heterogeneous policies. We are now currently exploring more about moving, I would say, closer to the second one, also learning high level. So at the end of the day, right now, they are very naive go-to allocation policies, and we are exploring how if you have a complex task that has multiple steps, a high-level specification, how to learn low-level policies from this, more from complex centralized to distributed. For heterogeneous, if you knew your role, I would say that the simplest solution, if you knew your role, you could have different weights for different roles. Another question is whether you knew or you want to decide which role to apply. But other than that, we haven't also tried what happens. Another good testing to see how this works, for example, in the competitive, let's let all of them run the same policy and see how it goes, this kind of thing, so that. But my guess is that as it is currently, it won't work on heterogeneous behaviors. Further research would be needed. This solution, maybe others. If you have some ideas, I'm also happy to discuss them. Yes?
Yeah, I was wondering the applications of all this model, whether you envision them to be specific.
Which one? The first or the second? Well, I forgot to relate to the online the questions, the others, sorry, yes. So applications, let's start well. The drone shows here definitely is a direct application, probably very simple in entertainment, but at the end of the day, our solution also is closed world in the sense that it's trained on .NET, but at the end of the day, I would say all these planning policies that we are seeing, maybe for manipulation for single robots, at the end of the day, the applications to multi-robot systems would be the same, no? Give me a task and then somehow generate the plan, the trajectory. And actually, well, I would say that policies, the way they work now, it's more a matter of what your diffusion policy learns is the set of actions. We are thinking something different here, no? Our approach is different in the sense that the denoising is the plan. So in that sense, I think that the potential applications of the first one are very big. Still many nuances and this is still at the very preliminary steps. As for the second, as I said, something that I really envision is that learning from demonstrations, complex centralized demonstrations, like this, learning these kind of behaviors. You can imagine a video here is the ship, but then we have the video of the ship or the video of driving, people driving. So learning distributed solutions based on that. And also, I would say that there is a mature field in terms of learning centralized policies. At the end of the day, if you don't care about distributed execution, I would say that that's an easier problem. So this can be seen, the first one, as some kind of learn to distribute a controller. And that's actually something very powerful. It's like, okay, we can have some coordinator that teaches, and then we have some demonstrations, and then we know, based on this global demonstration, how can we do, even if we don't have all the knowledge. So I think both are very promising in terms of potential applications.
So with the distributed controller, you could have dropouts or losses of agents and have other agents added back in. There's not a single central point of failure.
Yes,
Some mothership that you take down.
At the end of the day, all the properties of distributed solutions would apply here. And also the way that we design that is agnostic to the number of robots, definitely.
I have a question. In the first work they talked about the Hamiltonian formalism, have you thought about like multitask conditioning? I understood you were training a controller to do one task, but do you think of how to generalize
So
that?
that's one of the discussions that we are having, in the sense that here, let's say that you have a high-level task that has sequential multiple navigation goals, in the sense that go to here, do that, then come here, and how to learn, because at the end of the day, here it's also a matter of how to scale things. So we are considering how to scale that. We are considering curriculum learning in terms of maybe learn individual behaviors and somehow condition the policy on the high-level behavior. Actually, now that I talk about it loud, for your question about the heterogeneous, could be something like that. You can have an extra input about some kind of conditioning the behavior of the policy on something else. So we are exploring that idea, or maybe just something like the video of a couple of weeks, that you had a very long video, complex video, Rust talk, maybe something similar. Actually, we have way more demonstrations that they do to learn very, very simpler behaviors. Normalization.
Another follow-up question. Does the Port Hamiltonian formalism require properties on those learned matrices, the J and the R,
Yes.
to enforce passivity?
I didn't mention, but those are...
Enforce those at training time or after?
So I will say yes. The dissipation matrix needs to be positive semi-definite, and the interconnection matrix needs to be skew symmetric. So I didn't mention, but well, what you learn, it's not the matrix, but the triangular version, and then you have some kind of activation layer at the end to enforce these properties. And that's another property that I like about Hamiltonian. We were discussing, as opposed to maybe a classic AX BU, which makes maybe more sense. But the properties there, so for example, stability would be in the eigenvalues. Here, these kind of effects are relatively easy to achieve. There are still some communication. So, for example, for the skew symmetric matrix, you need the two blocks to be equal. So there is some communication, one communication round to make sure that the I with the J equals the J with the I. And also for the Hamiltonian function, there are some tricks there that right now we are doing by basic communication, but we have discussed how to learn them. Yes.
The solution that you have where they're all going towards a single reconstruction simulated airplane, this kind of assumes that once they've reached their goal, they kind of are in the steady state. Are they able to resist disturbances to the swarm? So if there's a large set of wind that kind of blows through and causes the part of the formation to be disrupted, can they reconfigure back into the solution? Or
Well, there are two things to consider here. Another thing that, from a robotics perspective, I don't like much about these generative models is that they are trained on a specific number of time steps. So basically, you cannot scale, or you need to do other tricks to scale time, which are not, it's not time agnostic. But so in that sense, I would say that probably if you have converged, you cannot, now you would need some kind of local controller to stay there. But let's say on line disturbances, I would say that Orca is a perfect example of how this handles this, in the sense that you have trained your model assuming that you are moving with a specific flow, and actually what we are doing is somehow considering as input of the step t a perturbed version of the t minus 1. But so in that sense, it shows the robustness. It's true that when you analyze, no, and we've also been talking about these models, and when you look about the inference algorithm, actually the basic algorithm also adds noise. No, it denoises and adds noise because at the end of the day, you are learning distributions, so it's a matter of considering this distribution. So I would say that probably that during the execution, not at the steady state, is an inherent property of these models. Yes?
You said you're sharing the state between agents, which consists of position velocity. Could you share higher levels information like maps or like segmentations or objects that the robots saw between the different agents?
Well, I would argue here that this is agnostic to the state that you want to consider, in the sense that as long as you have, well, I would say in the imitation learning, as long as you have the demonstrations of this state, you can consider anything. We consider just position and velocity because it was easy, but other than that, at the end of the day, it's like you have, in the imitation learning, you have your demonstration of x, your prediction of x through the rollout, the numerical integrator of the differential equation. So it can be x, it can be whatever. And actually another good property that I like about this is that opposed to, let's say, classic differential equation is like it learns. No, so well, we have the physical properties, skew symmetric, positive semi-definite, the Hamiltonian needs to be positive, and but other than that, it's like, so one would say if we are considering position and velocity or something like that, H, we could exploit some knowledge about kinetic and potential energy, right? Why not? Technically, yes, but something that I like is that at the end of the day, this is agnostic in the sense that it learns an H, whatever H, so it somehow is task agnostic. The important thing is that it learns the three matrices in such a way that the closed behavior is the one that you want to reach. Here I always like to make the analogy with adaptive control when you have some unknown parameter that you put some estimator, for example, to estimate the mass of an object. Typically, the estimator converges in classic and basic adaptive control systems. It converges to a mass that is close, but it doesn't converge necessarily to the right mass, but it converges to a value that somehow ensures that your control objective is satisfied. So more or less, this is the same idea here.
I don't know if I missed something simple, but how do you actually back out a policy or controller from this learned set of matrices?
So we use passivity-based control. At the end of the day, because of the Port Hamiltonian, what you can say is just you have the closed loop dynamics and the open loop dynamics. You put them together. No? You want the two equations to be equal, and you clear the loop.
Okay.
And there's some conditions from BBC. You know that there is some pseudo-inverse and whatever, but you take.
Okay. Let's go ahead and close it out. Let's.
Hello, and welcome to Introduction to Generative AI. My name is Dr. Gwendolyn Stripling, and I am the Artificial Intelligence Technical Curriculum Developer here at Google Cloud. In this course, you learn to define generative AI, explain how generative AI works, describe generative AI model types, and describe generative AI applications. Generative AI is a type of artificial intelligence technology that can produce various types of content, including text, imagery, audio, and synthetic data. But what is artificial intelligence? Well, since we are going to explore generative artificial intelligence, let's provide a bit of context. So two very common questions asked are, what is artificial intelligence, and what is the difference between AI and machine learning? One way to think about it is that AI is a discipline, like physics, for example. AI is a branch of computer science that deals with the creation of intelligent agents, which are systems that can reason and learn and act autonomously. Essentially, AI has to do with the theory and methods to build machines that think and act like humans. In this discipline, we have machine learning, which is a subfield of AI. It is a program or system that trains a model from input data. The trained model can make useful predictions from new or never-before-seen data drawn from the same one used to train the model. Machine learning gives the computer the ability to learn without explicit programming. Two of the most common classes of machine learning models are unsupervised and supervised ML models. The key difference between the two is that with supervised models, we have labels. Labeled data is data that comes with a tag, like a name, a type, or a number. Unlabeled data is data that comes with no tag. This graph is an example of the sort of problem that a supervised model might try to solve. For example, let's say you are the owner of a restaurant. You have historical data of the bill amount and how much different people tipped based on order type, whether it was picked up or delivered. In supervised learning, the model learns from past examples to predict future values, in this case, tips. So here the model uses the total bill amount to predict the future tip amount based on whether an order was picked up or delivered. This is an example of the sort of problem that an unsupervised model might try to solve. So here you want to look at tenure and income and then group or cluster employees to see whether someone is on the fast track. Unsupervised problems are all about discovery, about looking at the raw data and seeing if it naturally falls into groups. Let's get a little deeper and show this graphically, as understanding these concepts are the foundation for your understanding of generative AI. In supervised learning, testing data values, or X, are input into the model. The model outputs a prediction and compares that prediction to the training data used to train the model. If the predicted test data values and actual training data values are far apart, that's called error. And the model tries to reduce this error until the predicted and actual values are closer together. This is a classic optimization problem. Now that we've explored the difference between artificial intelligence and machine learning, and supervised and unsupervised learning, let's briefly explore where deep learning fits as a subset of machine learning methods. While machine learning is a broad field that encompasses many different techniques, deep learning is a type of machine learning that uses artificial neural networks, allowing them to process more complex patterns than machine learning. Artificial neural networks are inspired by the human brain. They are made up of many interconnected nodes, or neurons, that can learn to perform tasks by processing data and making predictions. Deep learning models typically have many layers of neurons, which allows them to learn more complex patterns than traditional machine learning models. And neural networks can use both labeled and unlabeled data. This is called semi-supervised learning. In semi-supervised learning, a neural network is trained on a small amount of labeled data and a large amount of unlabeled data. The labeled data helps the neural network to learn the basic concepts of the task, while the unlabeled data helps the neural network to generalize to new examples. Now, we finally get to where generative AI fits into this AI discipline. Gen AI is a subset of deep learning, which means it uses artificial neural networks, can process both labeled and unlabeled data using supervised, unsupervised, and semi-supervised methods. Large language models are also a subset of deep learning. Deep learning models, or machine learning models in general, can be divided into two types: generative and discriminative. A discriminative model is a type of model that is used to classify or predict labels for data points. Discriminative models are typically trained on a data set of labeled data points and they learn the relationship between the features of the data points and the labels. Once a discriminative model is trained, it can be used to predict the label for new data points. A generative model generates new data instances based on a learned probability distribution of existing data. Thus, generative models generate new content. Take this example. Here, the discriminative model learns the conditional probability distribution, or the probability of y, our output, given x, our input, that this is a dog, and classifies it as a dog and not a cat. The generative model learns the joint probability distribution, or the probability of x and y, and predicts the conditional probability that this is a dog, and can then generate a picture of a dog. So to summarize, generative models can generate new data instances, while discriminative models discriminate between different kinds of data instances. The top image shows a traditional machine learning model which attempts to learn the relationship between the data and the label, or what you want to predict. The bottom image shows a generative AI model which attempts to learn patterns on content so that it can generate new content. A good way to distinguish what is Gen AI and what is not is shown in this illustration. It is not Gen AI when the output, or Y, or label, is a number or a class of, for example, spam or not spam, or a probability. It is Gen AI when the output is natural language, like speech or text, an image or audio, for example. Visualizing this mathematically would look like this. If you haven't seen this for a while, the y is equal to f of x equation calculates the dependent output of a process given different inputs. The y stands for the model output, the f embodies the function used in the calculation, and the x represents the input or inputs used for the formula. So the model output is a function of all the inputs. If the y is a number, like predicted sales, it is not Gen AI. If y is a sentence, like define sales, it is generative, as the question would elicit a text response. The response would be based on all the massive large data the model was already trained on. To summarize, at a high level, the traditional classical supervised and unsupervised learning process takes training code and label data to build a model. Depending on the use case or problem, the model can give